In this video, I am going to go through the steps for you of calculating or analyzing doing a hypothesis test of the difference between the means for unemployment rates for 2016 versus 2015. The first step in that process is that you want to state your research question. Are the 2016 unemployment rates lower than the 2015 unemployment rates? Remember, this is a question about whether the population means are lower. We know that the sample means are lower, but we're really asking, is there enough evidence here to conclude that something about the fundamental forces causing unemployment rate levels has changed between 2016 and 2015? We would formalize that test mathematically as a test of whether the 2016 population mean is less than 2015. The alternative, which is always the version of the test that we would care about, should be stated mathematically as the 2016 mean minus the 2015 mean is less than 0. And so since we're taking a smaller number minus a bigger number, if we're correct, the smaller number minus the biggest number is going to give us a negative number, so less than 0. The null hypothesis, then, the one that we're actually going to test and see if we can reject, is that the 2016 mean minus the 2015 mean is greater than or equal to 0. And so that's what we're fundamentally testing. This is a left-tailed test because you always base your tails on the alternative hypothesis, and in this case, alternative hypothesis is that things are to the left. And so we can think graphically, I guess, in terms of that if things are far enough to the left, then we would reject our null hypothesis, and that would be clear support for the alternative. We're going to pick a 5% significance level. In this case, since it's a one-tailed test, it means that there will be 5% of the observations to the left of the statistic and 95 to the right. From a type 1 error standpoint, what this means is there is a 5% chance that we could reject the null hypothesis when in fact it's true. So a 5% chance we could reject the hypothesis that the 2016 mean is actually greater than or equal to 0, when in fact that's really true. Our rule for this, it's going to look very similar to the rule that we use for the one variable univariate test. In this case, though, because it's only a one-tailed test, it's probably a simpler rule. It is that if the T statistic is less than whatever we determine to be our critical value, or the p-value is less than p-critical value, we'll reject the null hypothesis. If they're greater than, we will fail to reject, and so there is a chance that the alternative hypothesis, or there's a chance that the null hypothesis is true. Sorry. In order to do this test, we need a few numbers. We need a degrees of freedom. Degrees of freedom in this case are the combined degrees of freedom of the two data sets. There's nothing about this test that requires that the two data sets have the same number of observations in them. Ours just happen to, but you could have different numbers, and you just add those two counts of how many they are and subtract 2. You also need a combined standard error. So just like in the original or the hypothesis testing we did before, we had a standard error that we basically took the mean divided by the standard error. In this case, we also need a standard error, but we need what's called a pooled standard error between the two samples, the two variables. And so we get that by taking the standard deviations of each of those samples, squaring it, and then dividing it by the number of observations in that sample. So we do it first for the 2016, then for the 2015. We'd add those two results together and take the square root of it. You'll see what that looks like over here in just a minute. Once we've gone through all of that, our test statistics, so our T stat, if you will, becomes the mean of 2016 minus the mean in 2015 minus the hypothesized difference. That's the numerator. We have that hypothesized difference. We'll set it to 0, but you could set it to any number if you wanted to test something other than 0. And then we take that whole numerator and we divide it by the standard error that we calculated up here, this pooled standard error. So let me walk through real quick and show you how that looks. First thing we're going to do is calculate the average for 2015. We'll do the same thing, equals standard deviation. We do .s because that is a sample standard deviation that we're dealing with for 2015. If you want you could just type in, we know there's 51. If you want to use an Excel formula, you go count, and you would select all of that data. Pretty easy. So, and then of course we can just drag these formulas over and it will recalculate that for 2015. So the first thing we want to do is we want to figure out our critical values, I guess. Critical value for the t values, we needed degrees of freedom. So we'll calculate that first. Equals, go back looking at the formula, it's just the counts from both observations, or both data sets, minus 2. And to get the critical values, we go equals t dot inverse. And what probability we're using is that 5% significance level. And the degrees of freedom are the 100 we calculated. Oops, sorry, that popped that up. And literally, this calculation, so it's a minus 1.66, this is a value that you would in a textbook, you might look up in the back of the book. And here we're simply calculating instead of looking it up. And so Excel's sort of looking it up for us, but otherwise there's nothing different. P-value is 5%. So we got to get this pooled standard error now. So again, equal to square root. We'll take this standard deviation and square it and divide it by however many observations there are. Then we'll add to that this standard deviation, square it. Oh, shouldn't be an equal, should be a plus. My bad. This standard deviation, square it, divided by however many observations there are. There we go. So, about a 0.20 standard error. So we're going to calculate our T statistic, and again, using the formula from over here, it equals mean of 2016, so make sure you get the 2016, not the 2015 first, minus mean of 2015, minus 0. I'm going to go ahead and type that in. It's a placeholder. You could put a different value in, but we just care about 0, divided by our standard error, gives us a result. So that's our t-stat. We can get the p-value of that by going t.dist, whatever that statistic is, comma, the degrees of freedom, comma. It's asking you whether you want the cumulative probability from this distribution. And for any of these kinds of analyses, yes, you do, so you type in a true. Okay, and so it says it's a p-value of 0.22. So now we have everything we need to do to actually calculate or decide. There's nothing else to calculate. We look at our t statistic of minus 0.78. It is not less than minus 1.66, so that would suggest to us that we fail to reject. We look at our p-value of 22%. It is not less than our p-critical of 5%, so we would fail to reject. So by failing to reject, what we're saying is that the population mean of unemployment rates for 2016 may in fact be greater than or equal to the population means from 2015. And so there's no real statistical evidence that unemployment rates have gone down this year. And that concludes this calculation part of it. I will do a little bit of a PowerPoint presentation and move this data over so you can see how I would explain the test in a separate video.